Hello, this is a question that is looking at some skills really more than anything else. So we're looking at graphs, looking at reading graphs. It's connected to the rates topic. So the first topic in paper 2 for chemistry. So I will just crack on with it, okay? So it says, question 1, a student investigated how concentration affects the rate of reaction between magnesium and hydrochloric acid. It says, this is the method used. Place hydrochloric acid in a conical flask, add magnesium powder, collect the gas produced in a gas syringe, measure the volume of gas every 40 seconds for 160 seconds, repeat steps 1 to 4 3 more times, repeat steps 1 to 5 with hydrochloric acid of a higher concentration. It then says, so if you just look at that method for a second, I'd be thinking to myself, if I got this question, I'd be thinking, well, how much hydrochloric acid do I put in the conical flask? How much magnesium powder do I put in the into the hydrochloric acid? Because remember, it's asked us to repeat this experiment 1 to 4 more times. It's asked us to repeat the step, 1 to 4, 3 more times. So if we want to do it the same, we're going to have to put some control in place, aren't we? We're going to have to put some control variables in place. So I would just be thinking that when I'd first read that method. Anyway, let's get on with the question. Figure 1 shows a gas syringe. What is the volume of the gas in the syringe? So luckily, because I'm on a computer, I can get a little bit closer. Obviously, you can get a little bit closer to your paper on your examination date, but we can see that this, let me just get my pen out, I beg your pardon. We can see that this here is 80, and we can see that this one here is 90, and we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 little markers between there. So that means that we've got a value of 10 between 80 and 90. So if we count up from 80, we've got 80, 81, 82, and our gas syringe here is at 83. So we know that our volume of our gas syringe is 83 centimetres cubed. That's fairly straightforward. Just remember, if it is a different value for each of the little graduations, then just make sure you work that out. But obviously in this case it was quite straightforward. It says, which 2 variables should the student keep the same to make the investigation a fair test? So we've got the concentration of hydrochloric acid, the mass of magnesium powder, the temperature of the hydrochloric acid, the time for the reaction to end, and we've got the volume of gas collected. So let's have a little look at our experiment again. It says, place hydrochloric acid in a conical flask, add magnesium powder. Well, literally, there is one that we were talking about before that we didn't know how much magnesium to put in, and we didn't know how much hydrochloric acid to put in. So we'll carry on going. It then says, collect the gas produced in a gas syringe, measure the volume of gas for every 40 seconds for 160 seconds. Repeat steps 1 to 4 3 more times. Repeat steps 1 to 5 with hydrochloric acids of a higher concentration. So our independent variable, the thing that we're going to be testing, is the concentration. So that's the thing that we're going to be changing, the concentration of the acid. So we know straight away, I'm going to just put IV, independent variable, is the concentration of the acid. We know straight away that this one cannot be our control variable because we know that that's our independent variable. Okay. Let's have another little look. We've still not got the volume of hydrochloric acid. We've not talked about that. But add magnesium powder. But how much magnesium powder? That's definitely going to be something that we're going to want to control. Now we call it, we never say the word amount, we always use the word mass of a magnesium powder if we're talking about a solid, how much of a solid, we use the word mass. Time for the reaction to end, that's already controlled. The volume collected, that is what we're collecting here, so that is our dependent variable. So we can put that as our dependent variable there. So we know that that cannot be our control variable. So the next thing that we can suggest would be, because we've not actually been given the volume of hydrochloric acid as an option, then the only thing that we could keep the same each time to make sure that it doesn't affect the rate of reaction would be the temperature of the hydrochloric acid. Remember, because they're the only two things that we've got left really, that's already been controlled. Time for the reaction to end, because it says obviously that we're only going to measure it for 160 seconds anyway. So they're the only two things that we have got then that's going to be able to use as our control variables. Another one we would definitely want to control would be the volume of our hydrochloric acid if we're changing the concentration. But it doesn't give that as an option, but that would definitely be another one that we would need to control. The next question says, the table below shows the student results for the experiment with hydrochloric acid of a lower concentration. So we've got here the time in seconds. So at 0 seconds, there was obviously no gas collected in any of the tests, so we get a mean of 0. At 40 seconds, we had in test 1, 46 centimetres cubed collected, test 2, 30 centimetres cubed collected, test 3, 47 centimetres cubed collected, and test 4, 49 centimetres cubed collected. And we have no mean calculated, we've just got an X there. We can see for 80 seconds, we've got our 4 tests for our 4 gas collections and a mean of 82. 120, the same. We've got 4 different tests, 4 different volumes of gas collected, and we've got a mean of 96, and the same for the last one. It says calculate the mean value X, so this one, in the table above. Do not include the anomalous result in your calculation. So that's quite kind, because it actually tells us that we're going to have to get rid of an anomalous result. So the word anomalous means a result that does not fit the pattern. It also says give your answer to 2 significant figures. So we're going to have to look at that when we come to our final answer. So we can see in test 1 we've got 46 centimetres cubed, test 2 is 30, test 3 is 40, and test 4 is 49. So we can see that this one here, test 2, is a long way off the other 3 tests. So we're going to class that as our anomalous result, and we are not going to include it in our mean. So I'm just gonna cross that out for now. So to calculate a mean, we obviously add all of those figures up. So 46 plus 47 plus 49, and then we divide the total of that by 3. I'll just put that into my calculator because I'm not very good at fast maths. Anyone that has me for chemistry will know that I don't do maths in my head very quickly. So it's 142 divided by 3 gives us 47.3. So we're going to put 47.3. That is the answer out of my calculator. But if we have a look, it says it wants the answer to 2 significant figures. So we've got, here is our first significant figure, is the 4. The 7 is our second significant figure. So that means we're going to look at our third significant figure and have a look and see if it's 5 or above, which it's not, it's 3. So we're not going to be rounding this up. So to 2 significant figures, our answer would be 47 centimetres cubed. And the fact that if it hadn't have said that in the question, if it hadn't have said give your answer to 2 significant figures, we would really have looked at the other means and say that they've been put to two significant figures here, like 82, 96. So we can see that it would have been to two significant figures. It then says, plot the data from the table above on figure 2. You should include your answer to question C, so the answer we've just done. And you do not, in this question, you do not need to draw a line of best fit. So that's quite good. That saves us a step, okay? So let's have a little look at the graph. So they've got our axes on already. Let me just make this a little bit bigger, a little bit zoomed out for you. We can see our graph is all our scale is done for us, which is really helpful. We've got on this y-axis, we've got the mean volume of gas collected in centimetres cubed, and we've got the time in seconds on the x-axis. So let's have a look at what our first plotting points are. I'm just going to get a red pen. So for 0 seconds, we've got a mean volume of gas collected as being 0. So I'm going to put our first point, a tiny little cross, in our origin. So we've got one there, okay? So 0 and 0. Let's have a little look at what our next one was. So we've got 40 seconds now, and we've got our x. Now we've just worked out our x as 47. So we've got 40 for our time in seconds and 47 for our mean volume of gas collected. So we're going along this x-axis to 40. We've got our 40, and then we're going to go up to 47. So this is where it might get a little bit tricky for a little bit trickier, should we say. So we've got 40, and we're going up in tens to 50. And we've got 5 little squares between 40 and 50, which means we've got each tiny little square just represents 2 centimetres cubed. So I've got to get to 47. I start off at 40, so I've got 40, 42, 44, 46, and my plot goes there. It goes between the 46 and the 48 at 47. Okay, that one's done. Okay, next one, we've got 80 and we've got 82. So let's have a little look at that one. Go back to here. So we've got 80, so we need to go to our time in seconds, which was 80, and we've got to go up to 82 for our second plot. We know that each one of these little squares is worth 2, so this is 80 here, 82 would be here. Okay, 82. Let's carry on. Next one, we've got 120 and 96. So let's have a little look. So we're going for our seconds, it's 120. So I'm here on this line here, and I've got to go up to 96. I'm going to go all the way up to 90. And then remember that each of these little squares is worth 2. So 2, 4, 6. We've got our 96 there. Okay. Then the last one, our last plot, is 160 and 100. So let's have a little look at what that takes us. So it's 160 seconds and 100 centimetres cubed of gas. So, I've actually forgotten what I just said. It's 160 and 100. So 160 seconds, we're here on this line here. And we can see that 100 centimetres cubed of gas is here. So it's not asked us to draw a line of best fit, so we're not going to do it, okay? But we can see that this line, if we were to draw a line of best fit, it would be a curve of best fit. And it goes quite steep at the beginning, and then it goes the line goes less steep until we get to around this point here of 80 seconds, and then it really starts to go a lot less steeper until it goes to the point where it's going to becoming quite flat, isn't it? We could see it might even start to flatten out a little bit. So it says figure 3, So we've done all we have to do for that point, for that question. It says, plot the data above from the table. You should include your answer to question C. We did that, and you do not need to draw a line of best fit, so we've not done that. Okay. Figure 3 shows the results of an experiment with hydrochloric acid of a higher concentration. So I'm just going to write here, this is our low concentration, just so I remember. This is low. And it says that this one is high. So let's have a look. High. Okay. High concentration. Okay. High concentration. It then says on this one, it says calculate the mean rate of reaction between 0 and 50 seconds. Use figure 3 and the equation below. So the main rate of reaction is the mean volume of gas collected divided by the time taken. And we've got to use this graph to help us. So in your exam, you would obviously have a pencil and a ruler. I don't have that luxury at the moment because I'm on a computer. So I'm going to do it with the best thing I can do with my little pens and hopefully like quite a steady hand. So it asked me to calculate the mean rate of reaction between 0 and 50 seconds. So if I go along the bottom here, I can see that my x-axis is the time in seconds, and my y-axis is the volume of gas collected in centimetres cubed, just like the previous graph. I can see that as I go along on the x-axis, each bigger square, okay, is worth 20 seconds. So I've got 5 little squares between 0 and 20. So I'm going to do 20 divided by 5 gives me 4. So I know that each little square is worth 4. And I've got to get to 50. So I'm going to go 40, 44, 48, and then that would be 52. So I'm going to go in between there. I'm going to go here. Now I'm going to go up very, very carefully. You are going to do it with a ruler and a pencil because you have that at hand and I do not. So I'm at 50 seconds here. My line's a little bit skewy. I do apologise. But I'm going to hit that line right there in the middle of 48 and 52 at 50. And I can see that at that point I have made 80 centimetres cubed of gas. So taking this equation here, I can see that I've got 80 centimetres cubed of gas, and it's took me 50 seconds to make 80 centimetres cubed of gas. So if I put that in my calculator, because I don't know what that is off the top of my head, again, not very good at fast maths, 80 divided by 50 gives us 1.6 centimetres cubed per second. So I've got 1.6, and I'm going to put 1.6 down there. Now for those 2 marks, you get those 2 marks, one for writing this part out and getting the information on the graph, and the second mark for getting the correct answer. It says describe how the rate of reaction, so use figure 3, describe how the rate of reaction changes between 0 and 160 seconds. So let's have another little look. So we can see here is 160 seconds. We can see that the rate of this graph is the gradient, okay? Because we've just done we've basically done the mean volume, so y, over the time, over x. And hopefully you all know from maths and from science that the difference in y over the difference in x is the gradient. So the rate is equal to the gradient of the graph. So what this question is asking us to do is to comment on what the rate is like by looking at the gradient of the graph. I do apologise, I'm not very good at this pen thing. Okay, so let's have a little look. So we can see that we've got a very, very steep line going, certainly going up to certainly for the first 20 seconds, it's a really, really, really fast rate of reaction. It's very steep gradient. Okay, between say 20 and 80 seconds, that really starts to slow down because the gradient gets less steep. And then as we reach 120 seconds here, we are no longer collecting any more gas, even though time is still going on. So we've reached 100 centimetres cubed of gas and we're not continuing to collect anymore, so that we can see that the rate has actually stopped there, the reaction's stopped. So we need to write that in sort of a couple of sentences that's worth 3 marks. So I'm going to take my pen off for a second. How do I write? Take the pen off. Get rid of that drawer. There we go. So I'm going to say, let's see what it was. So I'd say, okay, so maybe the first, certainly between 20 and 30 seconds. So like the first 30-ish seconds. So, for the first 30 seconds, the rate of reaction is high due to the steep gradient. Okay. Then we're going to say, so let's have a little look. So here if we look here, after 30 seconds, we can see that line's really starting to sort of, the gradient starting to get less. So we're going to say, after 30 seconds, the gradient becomes less steep showing the rate of reaction has decreased, so the reaction's gone slower. Okay, and then we can say at 120 seconds, well, probably before that actually, maybe 110 seconds, at 110 seconds, no more gas is collected and the rate and the reaction has stopped. 3 marks. Okay. It says the student concludes that the rate of reaction is greater when the concentration of the hydrochloric acid is higher. Why is the rate of reaction greater when the concentration of hydrochloric acid is higher? Tick 2 boxes. Well, you know that any reaction occurs because of particles colliding with the right amount of energy, the activation energy. So if we've got a higher concentration, it means that we've got more particles in a given volume, okay? So it means we've got more stuff in a given volume, so therefore we're going to have more collisions. So let's have a little look at the 2 boxes that fit that. So it says tick 2 boxes, the particles are moving faster. Well, we're not messing with the temperature, so the particles are not moving faster. If the temperature was increased, the particles would be moving faster and that would increase the rate of reaction, but we're not talking about temperature, we're talking about concentration. The particles have more energy. No, the particles don't have more energy. They have the same amount of energy, we've just got more particles. The surface area of the magnesium is smaller. No, we've not messed about with the surface area. We've just talked about the concentration, meaning more particles in a given volume. There are more particle collisions each second. Yes, there definitely are, because so if there's more collisions each second, that means we've got a higher rate of reaction. But because there are more particles in the same volume. So it's the two bottom boxes that we want to tick. It says the student tests the gas produced by bubbling it through lime water. No change is seen in the lime water. Give one conclusion that the student can make about this gas. Well, it's asking you about the 4 gas tests that you know. So the 4 gas tests that we know the test for carbon dioxide, the test for oxygen, the test for hydrogen, and the test for chlorine. The test for carbon dioxide is that it turns lime water milky. So although from this information we don't know what gas it is, we do know, because there's no change seen with the lime water, that it is not carbon dioxide. So we can say we know it is not, I can actually type this out rather than me doing this. But it is not carbon dioxide. Just to go through the rest of the tests. Test for hydrogen is we put a lit flame into the hydrogen and we get a squeaky pop. For oxygen, we put just a glowing flame. So one of the splints, when you've blown it out and it's still glowing, we put that into the oxygen and it will relight the splint. And for chlorine, it bleaches wet or damp litmus paper. I always say that in my class, that obviously bleach smells like chlorine, doesn't it? Like it smells like a swimming pool because there's chlorine in bleach, or there's a type of chlorine in bleach. And if you get bleach on your clothes, it bleaches your clothes. It turns them like a much lighter colour, a lighter, whiter colour. So that's the test for chlorine, is it turns a blue or red piece of litmus paper when it's wet into like a white colour, like a bleached. Anyway, let's get to the next question. The student tests the gas produced using a burning splint. Name the gas the student is testing for. Give the result of a positive test for this gas. So because it's burning and not glowing, it's got to be, from what we've just said, it's got to be hydrogen. Okay? If it was a glowing splint, then it would be oxygen. But because it's a burning splint, the name of the gas is hydrogen, and the positive result for hydrogen would be a squeaky pop.